All right. So, as promised, we're going to transition between geology and oceanography. And oceanography, basically, how this works is the subject of oceanography is broken down into four kind of sub disciplines. Okay, and we're gonna talk about each one of those four over the next couple of weeks. Okay, so today we're going to talk about the seafloor, which is also called geological oceanography. We're also going to talk about properties of uh, basically the chemistry of seawater. Okay, that's chemical oceanography. And we're also going to cover life in the oceans. That's called biological oceanography. Okay, and then next class period, which is after spring break, we'll talk about physical oceanography. So all that fun stuff like waves. So that's kind of how oceanography is structured. So we'll go ahead and get started. All right. So, um, I don't think this is anything that's new to anybody. You're seeing the names of the different oceans found on Earth. Okay. I'm sure we all have them memorized. But what I do kind of want to point out a couple of things that you may not know. Okay. The Pacific, of course, is the largest of the oceans, followed by the Atlantic. The Pacific is also the deepest, so it's the largest and the deepest. Okay. And you might have read in the book, uh, you might have seen rather in the book the term Southern Ocean used. Okay, as far as I understand, I haven't been able to get a clear answer on this whether or not the Southern Ocean is considered to be an actual ocean or if it's just kind of a term. But either way, what's called the Southern Ocean, they're referring to that little strip of land between the northern coast of Antarctica and the southern tip or the horn of South America, basically. Okay, and that includes the 60 degrees south latitude, which is the only latitude area on Earth that encompasses just all water. If you look at any other latitudes, going north from there, you'll notice that there's always some land if you're going in a circle. Okay, but this is the one place on Earth where you will, if you take a boat out on the 60th latitude south, you will never reach land. You'll just keep going around circles of water. So that's kind of cool. But just know that it's that little area of water that's referred to as the Southern Ocean. All right, so let's talk about uh, what makes up the seafloor. Okay, so before World War II, the seafloor was pretty mysterious. Okay, and you would think that by 1941 that we would know a lot. You know, we'd have a lot of advancements. We would know a lot about excuse me, a lot about the ocean. Okay, but we really didn't. Okay, and that's because we didn't have at that point the world did not have sonar. Okay, sonar, also called sound navigation and ranging, is just simply using sound waves to determine depth. Okay, but in addition to determining depth, okay, you can look at many different points that the sonar has already received data for, and you can compare the topography of land based on individual sonar, what they call pings. Okay, so how sonar works is basically you got a machine called an echo sounder. It's located on a ship. This machine sends sound waves down through the water column. Those sound waves hit the sea floor and they reflect back upward, and they eventually end up being picked up by the echo sounder again as the incoming wave, okay, sound wave. Okay, now what that does is the time it takes for the sound wave to go down to the bottom and come back up to the machine can be calculated to figure out what the water depth is to the seafloor itself. Okay, so with the advent of sonar, which, as you can imagine, was developed by the military to, I guess, facilitate sea warfare, okay, mainly submarine warfare. Okay, so a necessity at that point, especially with the big mean German U-2 subs. Okay, but anyways, yeah, like I said, basically it gives you a look at both the depth and just the general topography of the seafloor. Okay, but the only bad thing about sonar, traditional sonar, is that it only gives you a look at one little piece. Okay, in order to find out what the topography is of a larger area, you have to take many different readings and then extrapolate to get an idea of what the topography is. Okay, then what's called multi-beam sonar was invented later on, and what this does is it sends individual pings, uh, but it sends multiple ones at the same time. Okay, so each one of these lines that you're seeing is essentially one sound wave being sent down, but they're at different angles. So what you can see is essentially sonar is being used to kind of scan the ocean bottom rather than to just get one measurement. Okay, so each one of these rays it's the same concept where you have the sound going down, coming back up. It's measuring the distance or the depth, I guess, rather, and it's sending it back to the machine. Then the machine calculates how the topography looks. Okay, so this little thing here called a side scan can also be towed behind a ship, and that essentially can have its own multi-beam sonar as well. Okay, so you can get a whole lot of scanning done with this multi-beam sonar machine compared to the traditional sonar. Okay, so we really do owe it to sonar as the technique that really ushered in oceanographic exploration. Okay, and really that didn't happen until the 50s and 60s. Okay, like I said, the technology was new in World War II. Once the war ended and everybody got back, that's when things started to pick up on the research side, for like universities rather than the defense side. All right, so that's kind of a look at the history and how sonar works. So let me move on to the next subject. Basically, by using sonar, okay, we figured out that there are three basic provinces or kind of regions of every ocean basin. Okay, we have the continental margins. Those are always going to be close to the continental areas, both here and over here. Okay, so just notice that just like what we saw with the at the mid-ocean ridge, if you put like a mirror down the mid-ocean ridge, it looks like a mirror image on both sides, right? Yeah, same thing here. You put a mirror down the mid-ocean ridge, what you're seeing on both sides is each of these three provinces just as a mirror image. Okay, so we have continental margin, deep ocean basin, and then mid-ocean ridge. Okay, so I'll talk about each of those. But first we're going to start with continental margins, and basically continental margins include all land area from the beach environment all the way down to where the continental crust transitions to oceanic crust. Okay, so that's called continental margins. Okay, now continental margins can come in two different varieties. They could be passive margins or they can be active margins. The only difference is that passive continental margins are tectonically inactive areas. So that just simply means it's not a convergent plate boundary. That's pretty much what it boils down to. Okay. as a result, you wouldn't expect to see volcanism, earthquakes, much of maybe some very small earthquakes because they happen everywhere, but definitely not any volcanism. Okay, so the east coast of the U.S. is a prime example of a passive continental margin. Okay, if I, oh yeah, sorry, make sure I'm okay. I'll get to the active continental margin a little bit later. Okay, all right. So the main or predominant feature of the continental margin is called the continental shelf. Okay, and we briefly talked about this before. This is basically a very gently sloping area. It's the edge of a continent, of every continent. It slopes very gently in a downhill gradient to the point where there's a very sharp and abrupt drop off, kind of like a cliff. Okay. Um, that cliff represents the transition between the continental shelf and another feature called the continental slope. Okay, we'll talk about that next, but the continental shelf, okay? So some things about this. Um, every continent has a continental shelf, okay, though the extent varies. Sometimes the continental shelf is very narrow. Okay, that's pretty common on the west coast of the US where the continental shelf is really dinky and then it falls off quick. East Coast, the continental shelf is pretty wide. Okay, the Gulf of Mexico is actually all continental shelf. Okay, so as you can see, they can be vary in size. Can also contain oil, natural gas, other important mineral deposits. As you all are probably aware, the Gulf of Mexico has a lot of oil drilling. Okay, a lot of oil rigs out there in the shallow water. Also, continental shelf tends to be an area where a lot of former glacial deposits were deposited during the last ice age. But of course, they're underwater now, so we can't see them unless you dive down. But we know they're there. Okay, so because it's relatively flat, that's why we know that they're there. Plus, we've seen them by diving and all that good stuff. But also, in addition to glacial deposits, we know that there's also very thick accumulations of sediments. Okay, a lot of these sediments come from streams that drain out to the ocean. Okay, remember from our discussion of streams, we know that when water slows down, that's when the finest sediments will eventually drop out. Okay, because the slower a stream is running, the less capable it is of transporting big sediments, basically. So thick accumulations on the continental shelf, okay, also partly because it's relatively flat as well. Okay, so then we move out to sea a little bit, and we get to that point where there's that very abrupt cliff, okay? That's a steep seaward edge of the continental shelf, okay? That's called the continental slope, okay? So this is the area roughly where continental crust and oceanic crust meet, okay? And that's just I say that very generally because there's really no specific point at which that there's a clear transition. Okay, also this area is characterized as having very deep valleys cut through the continental slope, okay, into the continental shelf. And basically, that is from back in the last glacial period when sea level was a lot lower, okay, and streams, of course, ran out onto the continental shelf and then down the continental slope, okay, and that, of course, caused erosion of the very outside edge of the continental shelf where it meets the slope. Okay, so a lot of times you'll see very deep, steep V-shaped canyons there at the beginning of the continental slope. Okay, those are often referred to as submarine canyons. Okay, also at the foot of continental continental slope, okay, is a deposition feature called a turbidity deposit. Okay, and this is where we're transitioning from the continental slope to the next seaward feature called the continental rise. Okay, so this is where the slope is ending and it's turning into more flat again. So kind of right here, if you're looking at the diagram. So there's being that it flattens out from a steep incline, that means that we're going to see sedimentation there. And so that's exactly what we see. Oftentimes at the very downward edge of these submarine canyons, we'll see these layered sequences of different size sediments that are layered by size. Okay, these are called turbidity currents, or the rock, if it does form as a rock form that we haven't talked about, and it's pretty, you never see it because it's underwater. It's a rock called a turbidite, okay? It's a sedimentary rock that is graded. So you notice that when you get sedimentation, you get larger sized sediments deposited first, followed by the finer ones as you go up. Okay, that's pretty normal. You get the heavier sediments deposited first, followed by the finer, less dense ones later. Okay, turbidity currents are generally referred to as kind of like submarine landslides. Okay, because that's essentially that's kind of how they work. They work a lot like landslides. So that's partially why we see this specific sequence. But I'm going to leave it at that. We don't really need to get into the depths of any discussion of that nature. Excuse me. All right. So moving back to the continental margins, because this slide appears to be out of order. We looked at the passive continental margin. Okay, remember that was tectonically inactive. Now we're going to look at active continental margins. Okay, these are tectonically active margins of continents. Okay, so the west coast, especially the northwest coast of the U.S., this is a prime example. Though California is an active margin as well. Basically, this a active continental margin, you could pretty much just say is a place where there's a convergent plate boundary. Okay, that would pretty much sum it up. Okay, so this is an area where the continental shelf tends to be relatively narrow, and then the continental shelf, of course, ends at the continental slope, which is that very abrupt canyon-like appearance. Okay, but in this specific situation, the continental slope goes straight down into that accretionary, or the trench rather, the oceanic trench, where you have the one plate subducting beneath the other. Okay, so the continental rise just continues down into the trench, basically. One term that we did not, I don't think we really talked about in terms of the convergent plate boundary here, is one kind of unique feature, this thing called an accretionary wedge. Okay, basically an accretionary wedge is merely just sediment that's been scraped off of the top of the subducting plate and plastered up against the leading edge of the plate that's not being subducted. Okay, so as an example, okay, off of the coast of California, where there was once a subduction zone that resulted in these Sierra Nevada mountains that are there now, we had oceanic crust being subducted underneath the continental crust. Okay, so as the oceanic plate is subducting, the leading edge of the continental plate is scraping off the top of the sediments on top of the basalt, essentially, and they're kind of being plastered onto that leading edge. Okay, um, those sediments, okay, are being subjected to some pressure, typically not heat, okay, but they're subjected to some pressure, which means that they tend to deform. Okay, a little bit of deformation happening there. So this thing that's called an accretionary wedge basically turns into sedimentary rocks that are deformed. So a lot of the Los Angeles area, especially the closer you get to the beach itself, is basically a big accretionary wedge. And that's why if you're going down the interstates there, excuse me, freeways as they call them, you'll see, if you look up at the rock walls, you'll see a lot of deformation there. Okay, that is an old accretionary wedge. All right, so that's a look at the some of the features associated with the active continental margin. We've already kind of talked about these features, so I'm not going to belabor the point. Just remember these two features, the volcanic island arc and the continental volcanic arc, they form at convergent plate boundaries. Okay, the continental volcanic arc is that chain of linear mountains, volcanic mountains, that parallel the plate boundary, which concurrently is the same direction that the trench also goes as well. So I'm talking about the Cascades of today, okay, up in Oregon and Washington. Okay, so that's the situation where you have the oceanic crust being subducted under continental crust. When you have two oceanic crusts, you end up with what's called a volcanic island arc. Okay, remember that's that chain of linear island volcanoes that form parallel to the trench, but they form out in the ocean because when you get a convergent boundary that has two oceanic plates, that means it's in the ocean. Okay, it's not close to land. So hence, you're still going to get the production of the volcanoes. It's just they're going to emanate as volcanic islands rather than a volcanic mountain range on land. Okay, I'll go ahead and stop there. Are there any questions that anybody has on anything we've looked at so far? Okay. All right. So we just looked at the continental margins right here. Now we're going to move seaward and look at deep ocean basins. So there's one thing that you'll notice about deep ocean basins is they're flat, relatively flat. I mean, they do have occasional volcanic features that will spike up, but as a general rule, this area is just characterized as being very flat. Okay, this is where a lot of the most finest sediment that comes from land areas will end up depositing. Okay, hence the deep ocean basins, they're more like the top is more like a mud consistency because it's the finest sediments. It also includes a place, just generalized, that's called the abyssal plain. Okay, the abyssal plain is just kind of referred to as the area that's the flattest of the flat areas. Okay, so it's part of the deep ocean basin, but it's just kind of its own classification as the most Nebraska-like features of the ocean floor. So most flattest. Okay, so that's a deep ocean basin. Now, moving further seaward out to the middle of the ocean, we know that the mid-ocean ridge is there, okay? And we know that there's divergent plate boundaries at mid-ocean ridges, okay? So the mid-ocean ridge is that area where you have the two plates spreading, okay, diverging. And the reason why a mid-ocean ridge is slightly elevated, because if we go back to this picture, you can see here, we have the deep ocean basin here that's flat, and then we have kind of a hill-like appearance where the mid-ocean ridge is. Okay, why is that a hill-like appearance? Well, it's because the basalt is fresh, and it's fresh and warm still. Okay, so when basalt is freshly extruded as lava, of course, it solidifies and slowly cools down. At first, it's very voluminous in size because most hot things and warm things are more voluminous. Okay, that's just a general concept in chemistry where, like air, for instance, warm air expands. Okay, so over time, what will happen with basalt? It will cool down and it will contract. It'll essentially grow. The minerals will grow tighter, and so the rock will actually grow smaller over time. Okay, so that's why there's that kind of a ridge-like appearance. Let's see. Yeah, so I think I got that. So that's mid-ocean ridges. There's also features called rift valleys, where technically the mid-ocean ridge is a rift valley. Okay, a rift valley is really just that linear feature where you have a divergent plate boundary. Okay, but geologists often use the term rift valley to describe um, divergent plate boundaries that occur on land. Okay, but really it doesn't matter. Okay, it could be used either way. Um, so what's kind of interesting is in northeast Africa, where Africa meets the Arabian Peninsula, as you can see in this picture here, we actually have three segments of three different rift valleys that meet. We have the East African Rift Zone down here. We have the Red Sea, and we have the Gulf of Aden. Okay, they're all separating, as you can see by the red arrows, except this East African Rift Zone doesn't have the red arrows, but it is separating. I'll show you that. So basically, yeah, we have divergent plate boundaries here, and they're separating. So the Red Sea is getting bigger day by day, year by year, very, very small amount, keep in mind. Same thing with the Gulf of Aden. Okay, the Suez Canal, of course, is right up here. That's where the Red Sea is connected to the Mediterranean. So eventually what's going to happen is the Red Sea is going to continue to widen. It's going to break apart this area where the Suez Canal is and fully separate the Arabian Peninsula from Africa. And then this part of the East African Rift Zone is going to continue to diverge. This little chunk of land here is going to become just kind of like a big island off the coast, kind of like Madagascar is further down into Africa. Okay, so that's just kind of an example of an existing rift valley. That's kind of a cool example too. Iceland is another example of a rift valley on land, so that's also worth checking out as well. All right, so are there any questions on anything related to the seafloor? Okay, I want to spend more time on chapter 14. Chapter 13, as you saw, is pretty cut and dry. Chapter 14 is a little more complex, so let's go ahead and jump into that. Okay, but though it may be a little bit more complex, it is very interesting. I think you'll agree with that. All right, so first we're going to talk about temperature and salinity in the oceans. Okay, so first we'll start with temperature. So as you know, the amount of sunlight that hits any given part of Earth really depends on latitude. Okay, So that is to say that sunlight is more direct and more powerful at the equator than it is at the poles. Okay. At the poles, the sun is at a shallower angle, so it's more spread out, thus it's not as powerful. Okay. So keep that in mind as we go through here and talk about temperature. Um, Also, yes, we know that the equatorial regions are just warmer and the poles are colder. Okay, so just keep that in mind too as we talk about salinity. Okay, so salinity. Okay, very kind of fancy word just to describe the amount of mineral matter, dissolved mineral matter that's found in seawater, aka the amount of salt in seawater. Okay, really, when you break it down, if you look at this big pie chart here, you can see that uh, the majority, about 97% of ocean water is just water. Okay, about 3.5% on average is salts. Okay, salts of various composition. Okay, so you'll often see salinity referred to as this little sign here, like a zero. The zero would be a number, and then slash two numbers. Okay, that's one way that it's expressed. But to express it more easily and understandably, it's often just expressed as a percentage range. Okay, so like I said, average salinity about 3.5% by volume, though it does vary within the different oceans from 3.3 to 3.8%. So that may not seem like a lot, but actually, any minor changes in salinity can have pretty profound effects with ocean life. Okay, so just you know keep that in mind, especially as we later talk about like climate change. Very subtle changes can have big effects. Okay, so we see that the water is about 97% water, 3.5% salt. If we come down here to this pie chart, this is breaking up that 3.5% average of salts. Okay, so if we look at it, we're seeing that it contains mostly sodium chloride. Okay, about 85% ish, 86%. 86% table salt essentially dissolved. The remaining 14% ish is just other salts such as sulfate, magnesium, calcium, potassium, and then some other lesser ones. Okay, so as you can see, this in terms of salinity, it's not always just sodium chloride. Okay, there can be some other minor constituents as well. Not that it really matters. you you would have to do a chemical test to tell the difference, quite frankly. All right, so that's kind of what salinity is. Okay, so let's look at salinity by latitude because this is really where it matters. Okay, so in this chart you're seeing temperature and salinity behaviors by latitude. Okay, so the latitudes are going up and down. So, for instance, right here is the equator. Here is the North Pole. Over here on the right side is the South Pole. And what you're seeing is, with temperature, as you would expect, higher temperature in the equatorial region than the poles. Okay, but with salinity, it's not quite so clear cut as temperature, but I will tell you that the two are related. Okay, they follow each other essentially. Okay, now I'm going to go through and explain what's happening at the different latitudes here so that you understand why you have these squiggles. Okay, so first let's just go ahead and start with the poles, okay, because noticeably you can see that they are the two areas where the salinity is always the lowest. So here and then up here. Okay, the North Pole, it has the absolute lowest salinity of anywhere. Okay, but basically, um, the reason why the poles have the lowest salinity is because of two things. One is a low evaporation rate, okay? And that low evaporation rate occurs because of another reason, because they don't get as much sunlight, okay? Remember, the sunlight is angled at a shallower angle as you get closer to the poles. So therefore, the sun isn't as powerful, okay? So really, it's a combination of the reduced amount of sunlight that results in the low evaporation. That just means that um, you have more water in relation to salts. Okay. It just so happens that the North Pole is especially water rich compared to the South Pole. Okay, but both are still lower than any other areas. Okay, but it's lower than these two humps. I'll get to those two humps in a minute, but first let's talk about the equator. So it's higher than the poles, okay, and it's higher than the poles because that's where they get a lot of sunlight. It's very warm, okay. The sunlight is very direct, and as a result, there's a lot of uh, evaporation, okay. But what offsets evaporation is uh, greater precipitation that we see at the equator, okay, because we know that's where the rainforests are. So at the equator, it's kind of a mix where you have extra precipitation being balanced by greater evaporation caused by the more direct sunlight. Okay. Then we move to the two humps. Those are referred to as the mid-latitudes. Okay. Those mid-latitudes tend to be around 20 to 40 degrees latitude, north and south. Okay. Let's see. Okay. So the mid latitudes, the reason why you have those two uh, humps representing um, greater salinity is because of the way that airflow moves on Earth. Okay, and airflow, just remember, air and ocean water, they touch each other. They give each other moisture. They basically give and take moisture to each other. They interact. Okay, they're not in their own little spheres, and we'll talk a lot more about that when we talk about the atmosphere. Okay, so I'm not going to get into the specifics right now, but what you should understand at this point is that at the mid latitudes, what we have is sinking air, and sinking air typically is heating up and it's expelling its water. So sinking air tends to be drier. Okay, so the sinking of air occurs at the mid latitudes, so around 20 to 40 degrees latitude. Okay, usually around 30 degrees latitude is pretty typical. This is a latitude where if you look at a map of the world, you're going to see that a good majority of the Earth's great deserts are located along that 30-degree-ish latitude, both north and south. Okay, think, where's 30 degrees latitude in the United States? Right? It's Arizona, right? Southern California, areas where we have deserts. Okay, um, so yeah, that's just one example. So let's see here. I'm kind of getting off topic, but pardon me here. So yeah, so it's that dry air. Basically, the dry air is causing excess evaporation. Okay, We know that in deserts, evaporation is a constant threat because it's so dry. Any moisture you get, the air will naturally try to steal it away. Okay, and that's what's happening. Is so at the mid latitudes, you have the dry air is essentially stealing water, so evaporating the water. And when you evaporate water, what you're doing is you're increasing the concentration of water to salts. Okay, so you're taking away water. You're not adding any salts. You're just taking away water, and that's making it more salty. Okay. Same reason why the like the Dead Sea and whatnot, why they have so much salt is because of they're found in desert areas. Okay. And in addition to all this, salinity is also correlated with surface water temperature. Okay, so as you can see, with the when you start to talk about the peculiarities of the mid latitudes and the equator area, the general trend is that salinity increases with temperature. Okay, but like I said, you've got the weird things happening at individual locations, so those kind of throw it off. Okay. Before we move on to talk about the thermocline, are there any questions on salinity or temperature of oceans? Okay. Alrighty. We will move on then. So now that we know what salinity is, we can talk about how salinity changes, okay? But actually that's the next topic. First, we're going to talk about how temperature changes within the ocean, the water column itself. Okay, so these charts here show, it's kind of like a side view of an ocean, right? You're looking from the side. So you have the sea level up here at 0, and down here you see 3,000 meters. That means 3,000 meters below sea level, basically. Okay, so way down there. So what you see is this red line doesn't always look the same throughout the water depth, okay, from sea level all the way down to the bottom. Okay, and that's because of the effects of sunlight on the upper area of the ocean, the upper parts, upper waters. Okay, so basically, the effect of the sun warming the upper waters, essentially, it only reaches so deep, okay, before you get to the point where sun just doesn't penetrate down there, okay? And that's an area where you have this kind of transition of temperatures is called the thermocline, okay? Thermocline is an area where you have rapid change in ocean water temperature with increasing depth. Okay, so we have the effects of the sunlight warming the top waters here, makes them nice and warm. As we go down in depth, it starts to get colder and colder because the effects of the heat from the sun are becoming less and less. Eventually, you get down to a point where the change in temperature becomes negligible, and everything below that just remains the same temperature. Okay. So deep down, kind of just behaves the same. Kind of, you never see any changes deep down. Okay. Think of the thermocline as like if you've ever jumped into a natural lake. This is pretty common. You'll notice that your legs or your feet, whatever, are in an area of colder water, right? Because lakes they have thermoclines as well, where you have the warmer surface water, and then the deeper down you go, the colder it starts to get because of the decreasing effect of the sun's heat. So that's why your feet are cold, are in colder water, because yes, it actually is colder water, because the sun is probably just barely reaching down there to even warm it up. Okay, so that's the thermocline. Another thing to keep in mind about the thermocline is that it only develops when you have variations in temperature between the surface and below the surface. Okay, and by that I mainly mean summertime. Okay, summertime, when you have warm temperatures, okay, at the surface, and then you have cold temperatures below the surface, okay? Because year round, the deep ocean waters don't change temperature, okay, way deep down. They remain the same all year, no matter what season it is. But the surface waters are affected by the temperature increase of summertime. And so that's when you start to see that developing thermocline, okay? That's pretty typical of most places on Earth, most ocean areas, except for the polar regions, okay? Polar regions, so AKA the high latitudes, they typically do not develop a thermocline because, as we know, their summer times are very short, and the summers are still, quite mild. So there's not enough heat to really warm up the surface water enough in order to cause a change in heat, a change in temperature of the water. Okay, so that's why, yeah, typically thermocline is absent in the polar regions. Also, thermoclines in all the other regions, they tend to develop only during the summer, and then they'll go away during the fall, and they'll come back in the spring. Okay, so that's kind of how thermocline works. Okay. There we go. Okay. Very similar is the pycnocline. Okay. So if you were just to change temperature with density, just to swap out those two words, we're going to use the same exact concept of how they work. We're just swapping out the words. Okay. So pycnocline, a rapid change in water density with increasing depth. Okay, so how density works, density is driven by changes in temperature. Okay, so the two are inextricably related. Okay, they have a relationship there. But basically, cold water is more dense, warm water is less dense, and a pycnocline is only going to show up when a thermocline is present. Okay, because they're represented by the same exact waters. Okay, so when you have a rapid change in temperature from, let's say, waters between let's say 100 meters below the surface down to about whatever this is, 800. So between like 100 and 800, when you see the temperature drastically changing, that's that same water area that you're going to see the pycnocline. You're going to see that density change very rapidly as well. So they're not like two separate areas of water. They're just two different properties that reside in the same water. Okay, hopefully that makes sense. All right, so let me think here. Pycnocline. So basically, so that is to say that pycnocline is going to develop when a thermocline will. So summertime, okay, unless you're at the poles, okay, which is over here. So in the polar regions, you don't get any changes in the water density because there's also no changes in the water temperature. Okay, so I think that will do. Okay, I thought there was more, but that's okay. So, so are there any questions on the thermocline or the pycnocline before we move on? Because topics have a lot of moving parts. Okay. All right, so let's transition on from chemical oceanography to biological oceanography. And let me turn my phone off here. All right, so photosynthesis. Okay, that's something that we're all familiar with. Okay, so plants that convert sunlight plus CO2 plus water, and then they undergo that conversion, chemical conversion, to the waste product of oxygen plus glucose. Okay, it's the glucose or the sugar that is stored in the green stem stuff and leaves of the plant. Okay, so that's what the glucose is. But anyways, so photosynthesis is super important, of course, in the oceans. Typically, how it emanates is through algae. Okay, algae is one of the predominant reasons. I'm trying to think about where this producers of photosynthesis. Well, not really producers, but vehicles of photosynthesis. How about that? Okay, so photosynthesis also occurs only in the top waters of the ocean because that's where the sun reaches. You know, anything below, like, I think it's 100 meters or so, generally the sun doesn't get down that far, sunlight. So you're not going to see any photosynthesis below about 100 meters, but more so the closer you get to the surface. All right. So photosynthesis basically creates it's kind of like the bottom of the food chain, okay? And we're going to talk about that a little bit later here. But before we do that, let's talk about the different types of life, okay? So first is plankton. So plankton is just any life, plants or animals, that drift around with the currents, okay? So they don't have locomotion. That means that they don't move on their own. They are always moved by ocean currents, waves, etc. Okay, so this I'm mainly referring to algae and bacteria. Okay, so phytoplankton and zooplankton. Now, phytoplankton and zooplankton, okay, they are what feeds the larger multi-celled animals that are capable of locomotion, and those are called nekton. Okay, so any animal that's capable of moving independently of ocean currents and waves is called nekton. Okay, so fish, crabs, etc. Okay, then there's also kind of a sub or a unique classification also called benthos. This is any plant or animal life that lives on the bottom of the ocean. Okay, and by this I mean it can be the bottom of shallow water, like like the Caribbean. You know how if you go on a cruise or whatnot, you go out there swimming at the beach, you can see the bottom, right? It's pretty shallow water. Okay, benthos are animals that live at the bottom or burrow into the sediments of the bottom. Okay, but it also includes bottom areas of the deepest areas. Okay, so it includes both the shallow areas and the deep areas. The only difference, or the only thing that connects the two, is that they all live on the ocean bottom. Okay, so hence they're called bottom dwellers, whether they live deep down or right close to the beach. Okay. Okay, so that's a look at the ocean. Some real quick look at ocean life. So are there any questions on ocean life before we move on to talk about food? Okay, alrighty, not hearing anything. So let's talk about food here. So productivity refers to the rate at which food is made in the oceans, essentially. Okay, so what you're looking at is the technical definition, the rate at which organisms produce organic compounds in an ecosystem. Okay, it just means the rate at which food is made. Okay, so as we saw earlier, one of the ways that food is made, mainly glucose, is through photosynthesis. Okay, so photosynthesis is produced, as I said, essentially from solar radiation plus CO2 plus water undergoing that chemical reaction to glucose plus oxygen. Okay, then we have chemosynthesis. Okay, this is food that's produced by chemical reactions. Okay, this is a little bit different. So an example of chemosynthesis is that you have bacteria that, let's say you have bacteria that might be living close to the mid-ocean ridge, okay, and you get like seafloor vents where gases are coming up from the magma below. Those gases are often filled with some pretty nasty chemicals like sulfur, carbon dioxide, stuff that can really harm us pretty good. But you can get some bacteria that will undergo chemosynthesis. They will convert some of those nasty like sulfur compounds into food. Okay, so it's that chemical conversion is essentially what chemosynthesis is, and that's pretty common deeper down where photosynthesis won't work. Okay, so you're kind of seeing that kind of like a yin yang type situation. They work opposite. Okay, productivity is also influenced by the amount of sun, as you would expect, and the availability of nutrients. Okay, so nutrients really are kind of a building block for the production of food. Okay, nutrients are necessary for life in order to live. All right, so now we're going to look at productivity in the different latitudes of the oceans, okay? And we're going to see how they differ, okay? And that's what this chart is talking about. So, the chart looks pretty busy. There's a lot going on. So how I break this down is we're going to first look at tropical, or rather polar, then we'll look at tropical. Then lastly, we'll break down what they call the North Temperate. Okay. I refer to, well, what they refer to as the North Temperate, I typically just refer to as the mid-latitudes. Okay. So the mid-latitudes is really, it behaves based on seasons, different seasons. So we'll break it down by seasons. So starting with the polar oceans, okay, one misconception is that the polar oceans are devoid of life. Okay, that is wrong. Okay, there are a lot of nutrients that are stored deep down in the polar oceans, typically. Okay, and what happens is a lot of times most life doesn't really doesn't show itself until the warmer months, right? And basically what happens in the polar regions is it's not until the warmer months, so May through September, that you start to see animals consuming the nutrients that are available, okay? And so what happens in the polar regions is that because they have a very narrow summertime, right around mid-May, you see a very quick spike in productivity, so very quick spike in food production, and then it crashes very quickly down in through late August, okay? And that's pretty much it. The rest of the year is nothing, or very little. Okay, the reason why this occurs is kind of multifaceted. Okay, first is, like I said, because of the higher temperatures in summertime, also because of the lack of a thermocline year-round. Okay, polar waters, they never heat up enough, so that you have that transition of water temperatures. The water deep down is very similar in temperature to the water that's at the surface. Thus, a thermocline is never produced. It never occurs in the poles. Okay, and one other thing let me point out here is there's a lot, a lot to go with this stuff. Nutrients will get trapped beneath a thermocline. Okay, so nutrients are always found deeper down, like I said, and what happens or what causes the nutrients to move up toward the surface is called a process called upwelling. But really, I'll just explain it as ocean currents and waves, essentially moving around in the water, moving those nutrients with them up toward the surface. Okay, but when there's a thermocline in place, the nutrients will get blocked by the thermocline, and so they won't reach the surface. Okay, so keep that one in mind as we transition to the tropical one, because that's going to play a very important role. Okay, but that doesn't apply to the poles. Okay, because a thermocline doesn't develop here. Okay, so I got a little bit ahead of myself, but that's fine. So now we're going to talk about productivity in tropical oceans. Okay, so this, as you would expect, a thermocline is generally present year-round, especially the closer you get to the equator. Okay, and so what that does is that means that nutrients are generally trapped below the thermocline year-round, with some exceptions where maybe, for a couple weeks, let's say the water, the temperature, drops for whatever reason, and the water temperature drops as well, a couple degrees, that might start to break up the thermocline so that nutrients get through. But as a general rule, we have the thermocline present year-round, and the nutrients are being blocked beneath it. Okay, so that means that there's not a lot of food at the ocean surface in tropical oceans. And that sounds really backwards, right? Because you're sitting here thinking that tropical oceans are lush with life. Okay? And it is true, but it is also true that, yes, that there's a surprising lack of nutrients year-round. And that's why you're seeing this red line, which represents the tropical productivity, is pretty much flat year-round, with very minor upward blips once every season. Okay. So let's see here. Yeah. Okay. So I think I pretty much covered that. So pretty much year-round low nutrient concentrations in the upper waters of the tropical oceans. So to get nutrients, a lot of the life has to go down into deeper water if they can. All right. So lastly, we're going to look at productivity in the mid-latitude oceans, because this is kind of the oddball of the two. Okay, I will point out right now, this is associated with seasons. Okay, so we're going to go through the individual seasons and talk about what's happening. Okay, so this is the green line. So first we're going to talk about winter. Okay, winter, because the waters are cold, there's no thermocline. Okay, and naturally, because the waters are cold, and there's a lack of solar radiation as well during the wintertime, productivity tends to be at its lowest in the wintertime. But one thing I will point out is that even at its lowest in the wintertime, there's still more productivity in the mid-latitude regions than there is in the tropics. Okay. So wintertime, low productivity, thermocline is absent. Moving on to springtime, we start to go up to peak. Okay, so around mid-spring, we start to see the production of a thermocline. Actually, sorry, that's late spring rather. Okay, but before before that occurs, we reach a peak in the springtime, okay, for nutrient food production. So as winter turns to spring, temperatures are rising, right? It's getting warmer, therefore more food is being produced. That reaches a peak here right as the thermocline is beginning to develop. Once that thermocline develops, notice that the productivity starts to drop down as you go through summertime, okay? Okay. Then after summertime, start to get into fall. Fall time is where the thermocline is beginning to break up as the temperatures and the ocean water get cooler. So you'll notice a very brief uptick in productivity as the thermocline is breaking apart. Okay, more. And then winter time rolls in again, and of course the water temperatures drop. The amount of solar radiation drops, thus the amount of food being produced again drops. So it's a very, this is the rest here for summer and fall, very delicate process with the mid-latitude oceans and their food production. The key though is that the overall highest productivity in the oceans is in mid-latitude oceans. All right. So are there any questions about productivity in the oceans before we move on to a somewhat related but different topic? Okay. All right. So we just talked about the production of the food. Okay. Now let's talk about how food is consumed essentially by the life that exists in the oceans. So I'm going to talk about two different topics here. Well, actually three to be total. These two are kind of similar: trophic levels and food chain. Okay, so I'll start with trophic levels. Trophic levels are the transfer of energy, okay, from smaller organisms as they're consumed by larger organisms. Okay, so each time something big eats something smaller, that's considered a trophic level. Okay, and that's what you're seeing here in this chart. So we have sunlight produces algae, okay, aka the phytoplankton. Phytoplankton is consumed by the zooplankton. So zooplankton eats phytoplankton. Small fish eats zooplankton. Big fish eats small fish, etc. Each one of these steps upward is one trophic level. Okay, so it's that transfer of energy. Okay, I will tell you that this transfer of energy is very inefficient. Okay, between each step up, only about 2% of the energy is actually transferred. About 98% is lost. So not efficient at all. Okay, now somewhat related is the sequence in which food how to word this, the sequence in which basically who eats who. Let's word it that way. Okay, that's called the food chain. Pretty much the same process where you have zooplankton eating phytoplankton, small fish eating the zooplankton, big fish eating the small fish. It's basically a sequence in which bigger things eat smaller things. Okay, and with a food chain, it assumes that each animal within the food chain has a very select diet. So, AKA, big fish only eats small fish. Big fish doesn't eat phytoplankton. Okay. Now I'm going to compare that to what's called a food web. Food web involves essentially one animal, any given animal that lives out in the ocean. Rather than having a very select diet, it can actually eat many different organisms, thus having a more diverse diet. And that's evolutionarily beneficial because if one of these food sources suddenly gets cut off, it's really not a big deal. with a food web, because then this herring can just move on and eat something else that's within its food web. Okay, but if the herring only ate one specific type of fish, and if that fish went extinct, that would be a bad thing. So having a food web, having a very general diet is a very good thing from an evolutionary viewpoint. All right, so that's it for chapter 14. Yep. Are there any questions on anything that we looked at today with chapters 13 or 14? Okay. I'm not seeing any questions or hearing any questions. So I'll assume that nobody has any specific questions. All right, so then let me just kind of recap about scheduling. So get that midterm done by the 28th, this Sunday. Of course, next week is spring break, okay? Go out and light up the town. Just do it with a mask if you can, okay? Or just stay in like me and be boring. No, actually, like I said, I'm gonna go out and do some backpacking. But either way, it's time off. Get out there and enjoy it, even if you just go into your backyard. Okay, we will resume class on Wednesday, April 5th. Okay, and at that point, we will cover chapter 15. That's physical oceanography. Okay, so that's it. There are
Wait,
no
it's the 7th, right?
Sounds.
Oh, did I get that wrong? Oh, you're right. I'm sorry.
I just want to
You're
make
right.
sure we didn't have class on Monday.
Yeah, I'm looking at the wrong schedule here.
Oh, okay. Thanks.
Yeah, the 7th. That was my mistake. Okay. All right. Well, you guys have a good. Okay, I'll disregard your email. Yeah, I have a tendency to put my foot in my mouth a lot of times with scheduling things. But anyways, have a good spring break. And yeah, again, if you have any issues with the midterm, let me know. Okay, but get it done by Sunday.
Have a good one.
All right. Thank you. You guys too.